All right. Hi, guys. So, Mr. Hudeberg here. And rather than sending you off to somebody else for this information, I'm going to record the information myself here. So, as I said in class, we're going to focus in on something called scientific notation, right? And again, because we're using crazy big and sometimes crazy small numbers, we need to understand how scientific notation works. All right. So big and small numbers. So sometimes we deal with like huge numbers. So for example, the nearest star is a long way from the Earth. So here we have million, 100 million, billion, 40 trillion, 208 billion kilometers from Earth. That's a huge number. It's so big that our brains are not equipped to really know what 40 trillion, 208 billion actually is. That's huge. All right. Now, sometimes we're dealing with extremely small numbers. So when we're talking about things like atoms and the particles that make up those atoms, we're talking about crazy tiny things, right? So 0.0000167 kilograms, the mass of a single hydrogen atom. All right. Um, very, very, very tiny. All right. So why do we need to use scientific notation? Because sometimes there's just too many zeros and they're pesky. All right. So scientific notation is a way to abbreviate our numbers to make them easier to write and to work with. Right? So let's take Avogadro's number. We will learn about this later this year. It is a number very, very, very commonly used in chemistry to express how many atoms and molecules are needed to make up a certain quantity of something. And again, we don't really need to understand what that number means at the moment. But look at that number. That is a huge number, and you've got all of these zeros uh, associated with that number. And what we can do with scientific notation is make abbreviate that number using exponents in the power of 10 to write that number without worrying about all of those zeros, right? So the way we could write this extra huge number is like this. We could put the decimal right there and then express it as a power of 10 to indicate how many more decimal places we'd move to write that number in its long form, right? So it's much, much easier to write and use when you know how to do it, right? And it makes it so you're far less likely to make a mistake on your calculator because we're going to use these numbers in calculations. And if you're having to put 20 some odd zeros, high chance that you're going to put one too many or one too few zeros or one or two too many, right? And mess up your entire calculation. But if you know how to do scientific notation, properly and on your calculator properly, you're less likely to make those mistakes. So that's kind of why we need to do it. So when should you express a number in scientific notation rather than its long form? Here's going to be the general rule of thumb. When you get to 10,000 or bigger, right, let's put scientific notation. So anything greater than 9,999. Now, likewise, when we're talking really small numbers, anything less than 1/1000th, right, we're going to use scientific notation. Okay, I think that's just a good general rule to use. Now, technically, you could always use scientific notation. You can express any number in scientific notation if you want to. It's just that when we're talking about like 25, there's no reason to put that in scientific notation because it's easier to write 25 than 2.5 times 10 to the 1. So the reason we use scientific notation when we use it is really big numbers, we'll go 10,000 or more, and really small numbers, less than 1/1000th. All right, moving ahead, we're going to talk about what rules we use. How do we put numbers into scientific notation? So rule number one, right? So if we, let's go backwards here. We got the number 270,000 here. So we're going to express a fairly big number and then 0.000032, relatively small number. And we're going to talk about the rules we apply to appropriately put those in scientific notation. And rule number one is one single digit goes in front of our decimal. So here, our decimal's there and there. We're always going to put a non-zero number in front of the decimal. So putting 0 point doesn't count as that digit. It has to be a non-zero digit. That's rule number one. Two, we're usually not going to include those leading zeros, right? So we're essentially going to take those zeros off, and we're usually also going to remove our ending zeros, although not always. And there's rules for that that will come later in this unit. Okay, rule number three, we're going to count the number of places you move the decimal to determine the exponent. All right. So if it's a number that's greater than one, our exponent is going to be positive, right? If it's a number less than one, our exponent will be negative, right? And the exponent is determined by whether it's a 5 or a negative 5, for example. That's determined by how many places you had to move the decimal. So let's go back to this number 270,000, for example, right? So that can be expressed as 2.7 times 10 to the, whoops, 10 to the fifth, okay? So if I take this number, 270,000, and I put the decimal here, that means I moved it 1, 2, 3, 4, 5 places. That's why that's a 5. Now likewise, with 0.0032, to put the decimal here, I had to move it 1, 2, 3, 4, 5 places. But because that number is a small number, less than 1, we express that as a negative exponent as opposed to a positive exponent. All right, so here's some examples. Let's say we have the number 1,220,000. We're going to start with a single non-zero digit and then put our decimal. All right, we're going to include the twos, but we're not going to include those ending zeros in this case. So I'm going to go 1.22 times 10, right? Now this is a big number, so it's going to be a positive exponent. And because I'm putting the decimal here, it's 1, 2, 3, 4, 5, 6, 10 to the sixth. All right, same thing, although this is a small number. So my decimal is going to go right there. So 2.49. I'm not going to include those leading zeros, right? And I had to move the decimal 1, 2, 3, 4, 5 places. So this is going to be times 10 to the negative 5. All right, let's go an even bigger number. So, so we got, going to put our decimal right there. So 3.045. Now notice in this case, I'm going all the way out to my last non-zero number. Now we won't always do that, right? But for now, that's the way we're going to do this. And I'm not worried about the rest of those zeros, but I did need to include that zero right there because it's between non-zero numbers. Okay, so the decimal goes there and it's going to be times 10 to a positive exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10 to the 12th. All right, and last one, we're going to go 1.022. So our decimal is going there. And it had to move 1, 2, 3, 4, 5, 6 places times 10 to the negative 6. Okay, that's how that works. That is scientific notation. So we can also reverse this process. If we have a number in scientific notation, we just undo that, right? So I'm going to move my decimal 9 places to the right. So I'm going to go 3, 4, 0, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 4.5 times 10 to the negative 7. So I'm going to end with 4, 5, right? So the decimal started there. The first place over is there, so that's 1. So 1, 2, 3, 4, 5, 6, 7. 0.0000045. All right, we will practice this some more in class. I just wanted to introduce you guys to um, the process of converting numbers into and out of scientific notation. Now, we need to eventually sometimes correct incorrect notation. All right, so sometimes after a calculation, You get a number in scientific notation, but it's not written correctly. So what's wrong with this number, for example, is there are two non-zero digits in front of the decimal instead of one, right? So we would correct that by moving the decimal place one place to the left, all right? And so the correct way to write that, you'll notice that when we move the decimal to the left, my exponent got a little bit bigger. Moved it one place to the left, so our exponent went up by one number, all right? Now here, we would have to move our decimal to the right to make that correct. So the way we would fix that is, um, whoops, that should be an 8 there, not a 10, excuse me. Um, so because we move the decimal to the right, our exponent should get smaller. So we were 9, that would reduce that number to 8. Okay? Um, so we need to be able to correct an incorrect scientific notation by moving the decimal and then adding or subtracting the exponent appropriately. Or if we're not even in scientific notation when we want to be, we need to know how to convert it to. Or sometimes if it's in scientific notation, we want it out of scientific notation, right? We can do that as well. That is it. Adios.